Hello, this is Mrs. Taylor, and I'm going to introduce you to how to find the volume of a solid using the disk method. So the idea behind this is if I have a solid and I can represent the outline or the edge of the solid using a curve on the coordinate plane, and then rotate that region around an axis, so either the x or y axis, I can recreate that solid and then therefore use integration to find the volume of the solid. So I think what helps with this concept is a visual. So we're going to look at a butternut squash. It's a solid that has an unusual shape that we don't have a volume formula for. And let's say for whatever reason we want to find the volume of the butternut squash. So if you kind of look at it, place it on its side and place it on the coordinate plane, you can kind of somehow split it in half. It's not perfectly symmetrical, but it's close enough. And then you could just trace the outline or the outer edge of the butternut squash on the coordinate plane. And so the reason for that is now we have a curve on the coordinate plane that if I rotated it, I would get the general shape of the butternut squash. If you rotate it around the x-axis, and what I usually do to represent the axis I'm rotating around is just draw a little squiggly arrow like that to show that my x-axis is where I'm rotating. And that was not very clear, so I'm going to redraw it. So that just marks that my x-axis is the axis of rotation. And if I rotate this shape, then I get pretty much the equivalent of it down here, mirror image of it, not equivalent. And I get something that resembles a butternut squash. And it's three-dimensional because when I rotate that region, it fills that entire space. So the way this relates to calculus is it's sort of like cross sections. What we're going to do is we are still going to slice our butternut squash and find the volume of each slice. And so the idea is if I slice it this way, and you can slice it all the way down. We don't want to half slice our squash. But if I slice it over and over and over again, just like with cross sections, each cross section is going to be a circle, because if I rotate any region, any cross section will become a circle. And so in general we call these solids a revolution, and they all fall under the same category because their cross sections are always circles. And each of these circles by themselves, or these cross sections, could be seen as little miniature cylinders. And what we call them in calculus is disks, because when you think of a disk, you think of something much thinner than a cylinder. And so the volume of each disk will be the same as the volume of a cylinder, which is pi r squared h. And so the idea is that if I find the volume of each individual disk using this setup and then add all those volumes together, I'll get the volume of the butternut squash. And so it's a lot like cross sections, where we're using, instead of our area, we're using the volume of a disk as our general setup, but we're still going to use integration. And so let's say we have, this point here as our starting point of our squash, and this point here is our ending point. Then we would integrate from those 2 points the volume formula of a disk. And so our resulting integral would be volume equals pi times the integral from b to a. So we could label this as a, and that's a really rough looking a, sorry. This is a and this is b. And so from b to a, or a to b, the integral of the radius squared, so that's this r squared portion, and it's r of x because we are going to find an equation to represent this curve, and that would be your r of x because that marks the radius of each disk. And then it's squared because it's squared in the volume formula. And the dx represents the height of each disk, the change in x. So from this side of the disk to that one, that would be a dx. And so that would be how we would set up our integral to find the volume using the disk method, which falls under the category of solid to revolution. We take a region, we rotate around the axis, create disk cross sections, and then use that volume formula for the integral. So let's look at an example problem. So this problem is out of a book called Master the AP Calc Exam by Michael Kelly, and it's really a good straightforward problem to start with when learning about the disk method. So it says find the volume generated if the region bounded by f of x equals sine of x on 0 to pi is rotated around the x-axis. So it's always good to sketch the graph to get a feel for what your solid might look like. And so because I'm using the mouse to draw, I'll save you the artwork and I'll just graph it on the calculator. So if I graph this region on my calculator, I've changed the window from 0 to pi, so I'm just looking at the section of sine of x that they specified. And if I kind of imagined this region here being revolved around the x-axis, then what I would get is a little mirror image down here like this. So it's kind of like this stretched out orb looking thing. And so of course if I create my cross sections, I get circles or discs. And so I would use the setup that I just showed you. And so the volume would be equal to, and we pull the pi out front because it's a constant. We don't really need to let it affect our integration. And our limits of integration, they gave us 0 to pi. And then sine of x represents our radius, our distance from the axis of revolution to the curve or the edge of our solid. And so remember, it's radius squared, and that's the error I notice the most is people forget to square the radius. And then dx represents the height of the disk. So that would be my integral. And then to integrate this, sine of x squared or sine squared x isn't really an integral. We want to integrate by hand. And so what I'm going to do is I'm just going to use my calculator to find that integral. So if I go to math, option number 9 is the numerical integration option. I'm going to put from 0 to pi, and then sine of x. Oh, I need to put parentheses around that so that I can make it squared. I put it in the wrong place. And that would be squared. And then have my dx at the end. And I get 1.570, yada yada yada. And then of course I have this pi outside. I could have put it in the calculator, or I can just put times pi. And I get approximately 4.934. So this would be approximately 4.9. Ooh, that is terrible. Don't do that. 934. And remember, in AP Calc, you round to 3 decimal places, and you can truncate or round either way. And if you want to put units, you could put units cubed, but it's not necessary. So that is how you use the disk method to find the volume of a solid that's revolved around an axis.